Alright, so in this video I'm going to be explaining this paper, and it introduces this model GPL. So this paper, generative pseudo-labeling for unsupervised domain adaptation of dense retrieval. This paper in 2022 in Hugging Face and also University of Waterloo. So what is dense retrieval? These dense retrieval methods map queries and passages to a shared dense vector space and retrieve relevant hits by nearest neighbor search. So this is another, so we are going to be talking about another domain adaptation methods, still in the setting of unsupervised learning. So first you need to understand some background that what is this dense retrieval. As I said, these dense retrieval methods map queries and passages to a shared dense vector space. For example, in question answering, you always do this. So dense retrieval approaches can overcome lexical gap because, some words. So because it's a sparsity, some words are used more than others, so there is a sparsity. But in order to overcome this lexical gap and lead to significantly improved search results, we introduce dense retrieval. You should learn about it. However, they require a large amount of training data, which is not available for most domains. And this is, of course, one of the motivations of domain adaptation. Because, for example, in your source domain, you have lots of training data, labeled data, but in target, you have very limited number of data. And the nature of them is a little bit different, but still you want to take advantage of what you have trained in your source domain. So the performance of dense retrievers severely degrades under a domain shift. This limits the usage of dense retrieval approaches to only a few domains with a large training dataset. So we propose a novel unsupervised domain adaptation method, generative pseudo-labeling, which combines a query generator with pseudo-labeling from a cross-encoder. On 6 representative domain-specialized datasets, we find the proposed GPL can outperform an out-of-the-box state-of-the-art dense retrieval approach by up to 9.3 points. So the most common domain adaptation technique for transformer models is domain adaptive pre-training, which continues pre-training on in-domain data before fine-tuning with labeled data. However, for retrieval, it is often difficult to get in-domain labeled data, and models are applied in a zero-shot setting on a given corpus. Besides masked language modeling, different pre-trained strategies specifically for dense retrieval methods have been proposed. So far, ICT and CD have only been studied on in-domain performance. A large in-domain labeled dataset is available, which is used for subsequent supervised fine-tuning. And SimCSE, these models I have explained on the playlist for contrastive learning. These have only studied for unsupervised sentence embedding. So this is the performance of unsupervised pre-training. You see different data sets here, and you have different methods. and you get the performance of the pre-training methods with access to the target corpus as the training data. So if these pre-training approaches can be used for unsupervised domain adaptation, for dense retrieval was so far unclear. So in this paper, they transfer the setup from Wang 2021 to dense retrieval. And first pre-train on a target corpus, followed by supervised training on labeled data from MS Mark. So we have query generation, and then we give it to negative mining via dense retrieval. Then we provide pseudo labels using cross-encoder. So pseudo-labeling and cross-encoders. Biencoders map queries and passage independently to a shared vector space. Just like entity linking that I've explained, you either use bioencoder or cross-encoder, but bioencoder map queries and passages independently. But in contrast, cross-encoders, which is nicer, in my opinion, cross-encoders work on the concatenation of the query and passage and predict the relevance score using cross-attention between query and passage. Much more compact. So this can be used in a re-ranking setup where the relevancy is predicted for all query passage pairs for a small candidate set. So for a given target corpus, we generate for each passage 3 queries using T5 encoder-decoder model. For each of the generated queries, we use an existing retrieval system to retrieve 50 negative passages. Dense retrieval with a pre-existing model was slightly more effective than BM25 lexical retrieval. So for each query positive-negative tuple, we compute the margin delta. And you see is just the score as predicted by cross-encoder. So cross-encoder of query and P, your passage, cross-encoder of query and your passage, positive and negative pairs, and view synthetic data with marginal MSE loss. So to enable supervised training on a target corpus, because we don't have label, so synthetic queries can be generated for the target passages using a query generator trained on a different existing dataset. So previous work used a simple multiple negative ranking loss with in-batch negative to train the model. So P sub I is a relevant passage for query sub I, and sigma here is just a certain similarity function. And this tau controls the sharpness of the softmax normalization. And M here is just the batch size. So P sub I is just a relevant passage for this query. And we use marginal MSE, this loss, and this loss is a critical component of their model as it solved 2 major issues from previous QGen method. A badly generated query for a given passage will get a low score from the cross encoder. Hence, we do not expect the dense retriever to put the query and passage close in the vector space. So you see the evaluation for generative based domain adaptation. You get average of 50. For proposed method, which uses generative pseudo-labeling, you get slightly better. And this is an example of labels assigned to different query passages. For example, for the query, what is features contract, this query, it has one positive, passage, and then 4 negative passage. So for the positive one, we get 1, and the rest of them 0. For GPL, you see that it is 10.3, because GPL uses raw logits, which can be any value between positive and negative infinity.